There is no product rule for integrals, so we have to develop several techniques to integrate product of two functions or more. Here is a special product, and today we are going to focus on this very special one. So what is special about this product? Let's see. If you notice, this function is a composite function because it's f of g of x, so it's a function within a function. The inner function is g of x. But also, the second function in the product is what? Is the differential of the inner function. It's g prime of x dx. This product is familiar from the chain rule. I would like to recall d dx of f of g of x, which means the derivative of the function f of gx, which is a composite function with the inner function gx, is the derivative of the outer function f in gx times the derivative of the inner function g prime x. And I would like also to recall that to differentiate the composite function f of g of x, we use the substitution in which the inner function gx was the u. So to evaluate the integral of this specific product, we will use a u substitution for g of x exactly as we did in the chain rule. The u substitution is for the inner function of the composite function. So let's see how to do that. First of all, we will substitute u for the inner function gx. But if u is gx, then the differential of the u du is g prime x dx. So now I'm getting two birds in one stone. First of all, instead of f of g of x, which is a composite function, I get a simple function. It is just f of u. And also, I don't have a product anymore. Look at the new integral. This is just an integral f of u du, which is a simple integral with no product. To do this, I just have to find the antiderivative of f of u, which is capital F of u, and then obviously to replace the u again by g of x. Let's see how we are going to do integration by substitution in the case of the definite integral. First of all, because it has the same integrand, I'm still going to use the same u and the same du. But now I have a little extra work to do. I would like to change the limits of the integration. Think about the u equals g of x as a dictionary or translator. It translates from the x country to the u country. So, if you look at a and b, those are limits of the x. Why those are limits of x? Because this is an integral of the x. So I have to translate using the u equals gx to the u new limits of the integration. Here is what I get. The integrand is exactly as before, but now I'm changing the limits of integration. So if a was in the country of the x, then in the country of the u now equals g of a. And the limit b in the x is now going to be gb in the u. This new integral is an integral which is fully integral of the u. Please don't ever mix x and u in the same integral. To do that, we know what to do. You take the antiderivative and you substitute the limits of integration, and when you do this, you get your answer. But here is the useful one. It's really enough to get to this situation, because now we know what to do. So again, u equals gx is a translator from x to u. And I want to recall again The du and g prime x dx are the differentials of u and gx. It's very, very common for people not to write the dx, but this is an important part of doing any integration and also integration by substitution. Again, I will recall of another very common mistake. Don't ever mix x and u in the same integral. So if you look here, on one hand I have an x integral, and on the other hand, in the other frame, I have a fully u integral. Be specific more to check the limits of the integration if you have definite integrals, that indeed not only the function is a function of u and the differential, but also that you are writing the limits of integration as values of du's. Example. Let's integrate 2x sine of x to the power of 2 dx. So when I say the of, you already realize that this is a composite function. Okay, so this is a composite function, so it means that this is going to be the f of u. So with your permission, before I do anything else, I'm going to write it exactly as it's written up. G prime x dx is like the 2x dx. Okay, so what I need to do now is to have the u. Because you have parentheses and you already realized that the inner function of sine x to the power of 2 is x to the power of 2, this is an obvious du. Now when I have the u equals x to the power of 2, please take du, the differential, without looking at the integral. Because u is x to the power of 2, that's the only reason for du to be 2x dx. So this is the u. And we get everything now color-coded exactly as the rule of the u substitution is. So now I'm going to have a u integral only, so it's an integral of sine u du. We know the antiderivative of sine u is negative cosine of u, so we get negative cosine of u plus c, and the only thing left to do is to replace the u by x to the power of 2, and we get negative cosine of x to the power of 2 plus c. It's very easy to check. When you check those integrals, you will have to use the chain rule, obviously, because this is the antiderivative of the chain rule. Example. The integral of x sine of x to the power of 2 dx. First, let me shuffle the order of the two functions here, and the reason is because I want this to match more or less of what it's written above. So again, the composite function is exactly as before. If the composite function is exactly as before, the u has to be exactly as before. So there's no doubt that u is x to the power of 2. It's the only substitution that will make this function a simple function. Because u is x to the power of 2, du is 2x dx. But now I have a little of a problem here. I have x dx, which means I have not exactly the du. Oh yeah, but I can arrange that. Because if du is 2 times x dx, then x dx is du divided by 2. This is just half. Okay, now I'm ready to translate everything and to have a u integral. And I get that. Oh yeah, but du over 2 is 1 over 2 times du. So why not use the constant rule and get this guy out of the way? Now I'm doing exactly as before. The antiderivative of the sine u is negative cosine u. I have the 1 over 2 tagging along there and plus c. Now I'm replacing u by x to the power of 2 and I'm done. We're really lucky that the only twist on the original u substitution theorem is only manipulation of constants. Because it's always manipulation of constants, we always can take this constant using the constant rule and just take it out of the way by writing this in front of the integral sign and just continue as usual. Example. Now we have a definite integral. But if you observe this integral, we have exactly the same composite function sign of x to the power of 2. So this is a good reason to believe that the u is as before. So u is x to the power of 2. And du is 2x dx. Now we have to take care of the limits of integration. The limits of integration 0 and square root of pi over 2 are related to x. You need the translator g of x to transfer them to be limits of the u. When x equals 0, we are getting that u is g of 0, but g of 0 is 0 to the power of 2, which is 0. And what happens when x is radical of pi over 2? We have to square it, because g squares the x, and we get pi over 2. So now you know what to do. Here is the antiderivative, and we have to substitute the limits. So it is negative cosine pi over 2 minus cosine 0. Cosine of pi over 2 is just 0, and cosine of 0 is 1. So we get minus 0 minus 1. So the total is just 1.